Imagine throwing tennis balls at a wall with two doors. You might expect that some of the balls would bounce back, while others would pass through the doors. Some bounce back, but some pass through, creating a seemingly random pattern. Behind the wall, you see two distinct stripes of hits on a second wall, one behind each door, clearly showing where the balls have landed. Now, imagine ripples on a pond encountering the same two doors. The ripples behave differently than the tennis balls. The ripples pass through both doors simultaneously, creating an interference pattern on the other side. A complex arrangement of peaks and troughs where the waves overlap, forming a beautiful and intricate design. This seems straightforward, right? It's just the nature of waves and particles, but what if I told you that sometimes tiny particles like electrons behave like both the tennis balls and the ripples? They can act as particles and waves at the same time. This is the fascinating world of quantum physics, where the common sense rules of our everyday experience break down, and particles can be in two places at once, defying our usual understanding. This surprising behavior is known as wave-particle duality, and it's one of the most fundamental and mind-boggling concepts in quantum physics. It shows us that particles can exhibit properties of both waves and particles. It challenges our intuitive understanding of how the universe works and forces us to reconsider the very nature of reality, making us question what we know about the world around us. Quantum physics is the study of the universe at its smallest scales, the realm of atoms and the particles within them. Here, energy, momentum, and other quantities are not continuous but come in tiny, discrete packets called quanta. Classical physics, which governs the macroscopic world we experience, fails to explain phenomena at this scale. For instance, classical physics predicts that electrons orbiting an atom should continuously lose energy and spiral into the nucleus, leading to the atom's collapse. However, we know that atoms are stable, highlighting the need for a new set of rules. The rules of quantum mechanics. One of the key differences lies in the way quantum physics describes the state of a particle. Instead of definite positions and velocities, quantum mechanics employs the concept of probabilities, suggesting that a particle doesn't have a fixed location until it is measured. This probabilistic nature of reality is a radical departure from the deterministic worldview of classical physics. The strange behavior of particles at the quantum level is best illustrated by the famous double-slit experiment, a cornerstone in the field of quantum mechanics. In this experiment, individual particles like electrons are fired at a barrier with two narrow slits, creating a scenario that defies classical physics. If particles behaved solely like tiny marbles, we would expect to see two distinct bands of hits on a detector screen placed behind the slits, corresponding to the particles passing through one slit or the other, just as we would predict in classical mechanics. However, the experiment reveals something truly astonishing and counterintuitive. Instead of two bands, we observe an interference pattern on the detector screen, similar to the one produced by waves interfering with each other, suggesting a wave-like behavior. This pattern emerges even when electrons are sent through the slits one at a time, seemingly interfering with themselves, which is a mind-boggling phenomenon. This experiment demonstrates that particles, under certain conditions, exhibit wave-like properties, challenging our understanding of the nature of matter. Each particle doesn't simply travel in a straight line. Instead, its position is spread out like a wave, passing through both slits simultaneously and interfering with itself, a concept that is both fascinating and perplexing. This realization led to the development of wave-particle duality, a cornerstone of quantum mechanics, fundamentally altering our understanding of the microscopic world. But what does it actually mean for a particle to behave like a wave? This question lies at the heart of quantum mechanics and has puzzled scientists for decades. In quantum mechanics, the wave associated with a particle is not a physical wave like a water wave or a sound wave. Instead, it's a more abstract concept. Instead, it's a mathematical function called a wave function, which describes the probability of finding the particle at a particular location. This wave function is central to understanding quantum behavior. The wave function spreads out, similar to a wave, and its amplitude at a particular point determines the likelihood of finding the particle at that point. The higher the amplitude, the greater the probability. Where the wave function has a high amplitude, the probability of finding the particle is high, and vice versa. This probabilistic nature is a fundamental aspect of quantum mechanics. This is why the interference pattern emerges in the double-slit experiment. The wave-like behavior of particles leads to these fascinating patterns. The wave function of each electron passes through both slits, interferes with itself, and creates regions of high and low probability on the detector screen, forming the observed pattern. This self-interference is a hallmark of quantum phenomena. So, in the quantum realm, particles exist in a superposition of states, a bizarre concept where they can be in multiple states or locations simultaneously until a measurement is made. This superposition is what makes quantum mechanics so counterintuitive. This measurement collapses the wave function, forcing the particle into a definite state. The act of measurement itself plays a crucial role in determining the particle's final state. Section 5. Embracing the uncertain, the heart of quantum weirdness. The probabilistic nature of quantum mechanics has profound implications. It suggests that the universe is inherently uncertain at its most fundamental level. Unlike classical physics, where the future is predictable if we know the initial conditions, quantum mechanics introduces an inherent randomness. This inherent uncertainty is encapsulated in Heisenberg's uncertainty principle, which states that we cannot simultaneously know both the position and momentum of a particle with perfect accuracy. The more precisely we measure one, the less we can know about the other. This is not a limitation of our measuring devices but a fundamental feature of the quantum world. This fundamental uncertainty doesn't imply that the universe is chaotic or unpredictable. Instead, it suggests that the universe evolves according to probabilistic laws, where the future is not predetermined but unfolds through a series of possibilities. Section 6. Quantum physics in action, from lasers to teleportation. Despite its strangeness, quantum mechanics is one of the most successful scientific theories ever devised. Its predictions have been verified to incredible precision, and it underpins much of our modern technology. From lasers and transistors to medical imaging and nuclear energy, quantum mechanics plays a crucial role in our everyday lives. Quantum computers, which exploit the principles of superposition and entanglement, are being developed to solve complex problems that are intractable for classical computers. Quantum cryptography promises secure communication channels that are impossible to eavesdrop on. Beyond its technological applications, quantum mechanics has also opened up new avenues of research in fields like cosmology and astrophysics, helping us understand the birth of the universe and the nature of black holes. Section 7. Rethinking reality, the philosophical earthquake. The bizarre and counterintuitive nature of quantum mechanics has sparked heated debates among physicists and philosophers alike. The very act of measurement seemingly influencing the state of a system raises profound questions about the role of the observer and the nature of reality itself. Some interpretations of quantum mechanics suggest that consciousness plays a fundamental role in collapsing the wave function, while others propose the existence of parallel universes, where every possible outcome of a quantum measurement is realized in a different timeline. While these interpretations remain speculative, they highlight the profound philosophical implications of quantum mechanics, forcing us to reconsider our understanding of the universe and our place within it. Section 8. A universe of endless possibilities. Quantum physics, with its wave-particle duality, probabilistic nature and inherent uncertainty, paints a picture of the universe far stranger and more wondrous than we could have ever imagined. It challenges our classical intuitions and forces us to embrace a new understanding of reality, one where particles behave like waves, the future is not predetermined, and the observer plays a fundamental role. As we delve deeper into the quantum realm, we continue to uncover new mysteries and paradoxes, pushing the boundaries of our knowledge and challenging our very perception of the universe. Quantum physics is a testament to the power of human curiosity and our relentless pursuit of understanding the universe and our place within it, reminding us that the universe is far stranger and more awe-inspiring than we could have ever imagined.